Thank you very much. I would like to thank the organizers for the invitation to speak, and Richard, who's coming from breakfast right now for his 70th birthday. Hi, Richard. Hi. Morning.
You're not just checking up on me.
Well, sort of.
Checking in.
All right. So I am going to talk about some joint work with Dietrich Häfner and Andràs Vasy. For those late comers, it's on the linear stability of Kerr black holes. But the context is, of course, some nonlinear problems, so let me just introduce that. The very rough picture is that you're interested in the global behavior of solutions of the Einstein vacuum equation. And so that's just the equation Ricci of G is equal to 0. Einstein vacuum equation, where the object, the unknown G here, is a Lorentzian metric. And I'm going to adopt at least Dean's sign convention. Not sure about Alex's. So it's an indefinite quadratic form on each tangent space on obviously a 4-dimensional manifold M. And okay, so this equation has a bunch of very well-known, very simple, rather explicit solutions. There are sometimes oddly called exact solutions of the Einstein equation, even though, of course, as a mathematician, you always want to solve this equation exactly, but they mean you can write them down. So the first one is Minkowski space. And that's the situation in which the manifold can be written just as a time, so a factor of r, across 3 spatial dimensions x. And the metric I'm going to write as G sub 0, 0. You'll see in a few minutes why that. And the metric is just given by dt squared minus dx squared, or in polar coordinates in R3, dt squared minus dr squared minus r squared times the round metric on the 2-sphere. Okay, so that's the unique, up to topology, completely flat solution. Okay, so the next solution, so this was found even before this equation was written down by Einstein. Some people are just ahead of the game. So then the Schwarzschild spacetime is the following manifold. It's very similar. You just cut out, say, r equals 0 in polar coordinates. Let's just write it as a factor of time again, cross 0 to infinity in r, and then you have a 2-sphere floating around. And the metric in this case, let me write as G subscript m, 0. So it depends on a parameter little m. And you can also write it down explicitly. Let me just do that. So it's 1 minus 2m over r dt squared minus 1 minus 2m over r reciprocal dr squared minus, again, r squared times the round 2-sphere metric. Okay, so one thing to point out here is that this metric is just a small perturbation when you're far away from the black hole, which you think is at r equals 0. So when r is very large, this is just a 1 over r perturbation of the Minkowski metric. So asymptotically, as r goes to infinity, this looks very similar to Minkowski space. Close to r equals 0, or even at r equals 2m, this form of the metric breaks down. You have to do some coordinate change, which I'm going to not do here, to extend it beyond this coordinate singularity at r equals 2m. So strictly speaking, this is a slightly different coordinate system. Okay. Okay, so this solution here is in fact the unique. Okay, let me actually say. So m here is some positive number, and it's the mass of the black hole. So mass of black hole. And this is the unique family of spherically symmetric solutions of the equation. So it's an extremely natural object. The third family of solutions I want to write down is yet a generalization of this. It's called the Kerr spacetime, or Kerr family of spacetimes. And it's the same manifold, give or take. And the metric now I will not write down explicitly, even though you can do so. It's not too bad. But if you look at the expression, it's equal to the Schwarzschild metric plus some extra correction terms which decay even faster, like 1 over r squared. And so what are the parameters here? So m and a are a real number and then a vector in 3-dimensional space. And a here is supposed to be the rotation axis. That's the direction. And the length of it is the angular momentum. And the slowly rotating in the title of my talk just means that this angular momentum is very small compared to this other parameter, compared to the mass of the black hole. So this is supposed to model a, so this is, the Schwarzschild metric is a black hole of mass m that's just spherically symmetric. It's not rotating. It arises by the gravitational collapse just of a spherically symmetric star, if you will. And the Kerr spacetime is the end product of the collapse of a star that's just ever so slightly spinning around some axis. Okay, so these are all solutions of the Einstein vacuum equation, and they have some extra property, which I'll write down in a second. So a useful thing for discussing these metrics as a family of metrics is if you can actually realize them as metrics on a fixed spacetime, so then you just make that completely precise. So let's just fix your favorite mass parameter m0, some positive number. And let's define a manifold M to be, well, time cross space, x naught. And so space here, let me just be slightly more honest and take some half-infinite interval from some radius r minus to infinity to s2. And r minus is less than 2m0, but bigger than 0. So I'll draw a picture of this in a second. And OK, so you can now realize on this fixed manifold, so on M, this family of metrics, depending on mass and angular momentum, is a smooth family of stationary Lorentzian metrics. OK, so stationary just means that there's a time-like killing field that Alex also used in his talk. So the Lie derivative along d by dt of all these metrics is equal to 0, or even more simply, the coefficients of the metric are time independent. OK, so and here, just for this talk, let me just restrict the parameters m and a to be close to those of the Schwarzschild black hole with mass m0. So M and A are going to be close to M0 and 0. OK, so we just look at Kerr black holes that are of mass close to M0 and just slightly rotating in your favorite axis. OK, so let me just draw a quick impression of what this metric looks like. So let's take B0 to be the Schwarzschild parameters. And let's draw a picture of the spacetime for the metric GB0, just to give you some impression of how these spacetimes behave. So you have some time direction t, and you have some r direction. And so here's the spacetime now. OK, so you start at r minus. Then there's this line here where the radius parameter is equal to 2m, equal to 2m naught. So this is somewhere where one has to do some coordinate change to actually make sense of this metric. OK, and so I just declared my spacetime to end right here. And what happens, why this space here is actually special, is if you look at the light cones of this metric, which determine, on the one hand, of course, where singularities propagate, on the other hand, also where just the support of solutions of a wave equation can spread along. So then if you're far out here, the metric looks like Minkowski space. So the light cone is just looks like that of Minkowski space. If you're close to the event horizon, then it already gets quite tilted, so it's very hard to get away from the black hole, but it's very easy to fall towards it. And once you're on the other side of this, this dashed line here, then no matter how hard you try, you're always going to be moving more towards r equals 0, towards the center of the black hole. Okay, so this dashed line here is the event horizon. It's the point of no return. That's what makes it a black hole. But very far out, it just looks like Minkowski space. So like your good old Minkowski space. Okay, so given that this is a conference in honor of Richard, of course, I'm going to compactify this picture a little bit at various places. But I'm just going to do it somewhat sketchily. So one thing about waves on such asymptotically Minkowskian spacetimes is that one interesting regime is when you go out radially outward as far away as possible from the black hole. So you somehow follow along these kinds of outgoing directions. And then what you will hit is, in a suitable compactification of this spacetime, null infinity, or the radiation field. Okay, and so a parameter along this here is something like, let's call it T star. It's essentially T minus R, right? This is what it would be for Minkowski space. But for a Schwarzschild spacetime, there's a slight correction factor, addition. It's not too important for my talk today, but it's something like logarithmic. Okay. So that's that. And T star goes to minus infinity over here, to plus infinity over here. All right. So then if you live in the present and just look at what the spacetime does at t equals 0, that's down here. So let me call this sigma. So this is the universe, the Schwarzschild universe fixed at time 0. Then I can compactify this here as well. And so a boundary defining function would be something like rho inverse, r inverse equals rho. Okay, so this is just a compactification, radial compactification of R3. And then I can connect these two things here. Okay, it's not too important how that goes. Okay, so this is some of the far end of the spacetime. But then, of course, what's most interesting is what happens close to the black hole. And so here we just compactify time. Okay, so a boundary defining function of future infinity is just 1 over T star. Okay, so T star is equal to T over here. So you're just measuring decay relative to inverse powers of T. Okay, and so along here, of course, R is still a perfectly good coordinate. Okay, so this is the rough picture. And solutions of wave equations will then be really boring over here. You will have a radiation field over here, which encodes a lot of interesting information about energy radiated away. And then what you see over here on this so-called future time-like infinity is some of the final state of evolution of whatever equation you're looking at, close to the black hole. Okay. So to give this a little bit more substance from the point of view of the Einstein vacuum equation, let me just remind you of the initial value problem. And so that takes the following form. You're given two pieces of data at this initial moment in time. So you're given gamma, which is a Riemannian metric on sigma. And you're given another symmetric 2 tensor K. So these are the two data. And what you want is to find a Ricci flat metric. So find G on the spacetime M, let's say, which is Ricci flat, and attains the initial data in the following sense. So we call it tau, the map that takes a metric to its initial data at sigma. So how are the initial data measured? Well, you restrict, or rather pull back the metric G to your hypersurface sigma. That's one piece of data. And the other piece is sort of the first derivative of G across sigma. And so that's the second fundamental form of sigma with respect to G. And you want this to be equal to the two pieces of data, gamma and K. Okay, so it's a geometric initial value problem. And okay, so it's been long known by Choquet-Bruhat that a necessary and sufficient condition for the at least local solvability of this initial value problem near sigma are what's called the constraint equations. And I'm not going to write them down, I'm just going to give them a letter. So C of gamma and k equals 0. And they're just the Gauss-Codazzi equations for the geometric data induced on a hypersurface inside of a Ricci flat ambient spacetime. So it's some nonlinear second order, I suppose, system of PDE for gamma and k. Okay. So now, in general, of course, the problem that I just erased, understanding the global behavior of all solutions of Ricci g equals 0 is, of course, somewhat absurd. So the best one can do is to study, at this point, perturbations of, say, one of these special solutions here. So to formulate this, let's just call the initial data of such a Kerr metric as follows. So let gamma sub b and k sub b denote the initial data of a Kerr metric, G sub b. So b stands for black hole parameters. So it's M and A. Okay. So then one of the main open problems in the field at this point is the Kerr stability conjecture. Well, Kerr is a person, so one should probably call it the Kerr black hole stability conjecture, because Kerr is still very much kicking and just got elected, I think, to the Royal Society of Fellows. Is that right? I think so. So let's put in a black hole here. Okay, so.
He's quite a stable person.
Yeah, I heard so. Yeah. Okay, but his black holes, we don't know. So, okay. The conjecture is the following. So. At least in the slowly rotating case. So let's start out with initial Kerr parameters b sub I initial. So it's some initial mass and initial angular momentum, and let's say they're close to that of our preferred Schwarzschild black hole. So in particular, slowly rotating. And then we're given initial data, gamma and k, on sigma, of course satisfying the constraint equations. Which are close to the data of Kerr in the following sense. So I'm just going to make it very rough. So the difference of gamma and gamma sub bi, so the initial data of the Kerr black hole, are, let's just write it like this, less or equal than some small constant epsilon times r to the minus 1 minus, I don't know, some number alpha. So you want them to be small and also decay at infinity so that the initial data look like those of, say, Minkowski metric. And then you also have a similar fall-off condition on the second fundamental form, something like this. And alpha is some positive decay rate. Of course, you want this with a whole bunch of derivatives, but because it's a conjecture, so I can claim that this conjecture is false. But if you add some more derivatives, we don't know. Okay, so then given these initial data, there exists a solution G of the initial value problem, which moreover has the following form. So there exist two things. So a solution and black hole parameters b sub f for final, which are close to b sub I, so that the solution of this initial value problem G is equal to the Kerr metric with these final black hole parameters, which in general will be different from those of the initial black hole, plus some error term G twiddle. And this error term G twiddle here decays like, well, let me say T star to the minus beta for some constant beta, presumably depending on alpha. Okay. So this is saying that the endpoint of the evolution of initial data that are close to one of those particular Kerr black holes is again a Kerr black hole, perhaps a slightly different one, perhaps some gravitational wave energy somehow fell into the black hole, made it fatter. And then you have this radiation term G twiddle, so the black hole settles down at some inverse polynomial rate to the final Kerr black hole. Okay, so for those who happily work with radiation fields. So somehow this is just to indicate that, okay, there's going to be something interesting radiating out to infinity. But what somehow most interesting is to figure out how the radiation field behaves as you go out towards future time like infinity. So this is somehow decay of a radiation field and also decay of the metric close to the black hole. Okay. So I'm writing here, there exists a solution. There's actually a caveat in there, namely solutions of this Einstein vacuum equation are very much non-unique, because any solution can be pulled back by a diffeomorphism that, say, fixes the initial surface to second order or something. And you still get a solution of, so upon pulling back this metric by this diffeomorphism, you get another solution of this initial value problem. Okay, so you have to somehow pick a gauge to get rid of this diffeomorphism variance in order to even start sort of looking at this conjecture analytically. Okay, so for prior work, the body of work is extremely big on these kinds of problems, so I'm just going to be rather terse. So the first thing is some shameless self-promotion. Because Andràs and I proved, so it was published in 2018, the stability of Kerr de Sitter black holes, which probably most of you have seen either Andràs or me give a talk about at some point. And in this case, you're not solving the Einstein vacuum equation, but something with the cosmological constant. And in this case, the decay rate of this tail here, this gravitational wave tail, is actually exponential. So something like e to the minus beta t star. Okay, so this is a very big difference to polynomial decay. And ultimately, the reason will be due to the fact that very far from the black hole, these Kerr black holes are asymptotically flat spacetimes. So spectral theoretically, you have to look at an asymptotically Euclidean resolvent, which has notoriously bad properties near zero energy in particular. So the resolvent has some finite regularity there and so on. Whereas in this case, it looks more like an asymptotically hyperbolic problem far away. And for that, the structure of the resolvent is much, much better, like Matteo Melrose and Vasy and so on. Okay, so I'm going to talk a little bit more about that. The second one is a proof of this conjecture in a special symmetry class, which recently announced by Kleinerman and Seftel, I think also 18. So that's the proof of this conjecture for a special symmetry class. So it's so-called axially symmetric polarized symmetry, which excludes in particular that the final black hole attains any angular momentum. Okay. So let me just point out a few main issues that one has. Well, first of all, before going into the field of relativity, and then once you're in it when trying to tackle this problem. So the first one, as already indicated, is the diffeomorphism variance. Okay, so that requires you, if you want to do analysis, to fix a gauge. I'll talk just a little bit about this. Okay, so gauge fixing just gives you extra conditions on the solution G on the spacetime M that you want to impose in addition to being Ricci flat, which will then pin down the metric more or less uniquely. But even then, once you have fixed a gauge, it could still happen that you start out solving your initial value problem, you just start a little bit, and then you see that the black hole somehow is trying to get away somehow from the center of R3. It may start somehow moving away in the gauge that you fixed. So you still have to somehow track the center of mass of the black hole. I mean, being somewhat vague here, what is the center of mass and so on. But you just have to, I mean, you want to show that something decays to a Kerr black hole. So you have to know where is that final Kerr black hole even ending up in order to be able to compare the solution G that you find with that final Kerr black hole. Okay, so this is an important problem. And another problem is, of course, that there's no known way to compute just the final mass and angular momentum of the black hole. It's a very nonlinear process that somehow energy can radiate away to null infinity, and thereby decreasing the mass and so on. So it's not just some simple integral over the initial data that you can compute to get the final mass and angular momentum. Okay, so these are two of the main issues. And so to justify the rest of the talk, let me just very naively talk about how one can try to solve this nonlinear problem, so very naively. And sort of the souped-up version is what worked in my work with Andràs. So you can set up, just like Jesse's child, I think, suggested to him, an iteration scheme, right? So Jesse's child told me, start with G0, which is the initial metric you're perturbing. And then you just try to improve on this. So this solves the Einstein equation, but it does not attain the correct initial data. OK, so then you just linearize the equation you want to solve around your current guess G0. And you want to find some symmetric 2-tensor H0, which satisfies the equation, whatever error I'm making. Right, so at the first step, this is just equal to 0. There's some kind of Newton iteration. And then, of course, you also want to impose initial data on H. OK, so suppose you could solve this equation. There are many issues with this particular formulation. But if you could, you would then just say, well, my next best guess at the solution of the nonlinear problem is G0 plus H0. And then you try to keep just iterating this scheme. OK, so notice that in the very first step of this iteration scheme, what you're looking at is the linearization of the Einstein equation around a Kerr metric. Because in the very first step, you already have to study this linearized problem of stability around Kerr. OK, so that's what I'm going to talk about. But then if you go on later in the iteration scheme, it's not that this linearized problem somehow becomes completely irrelevant in the second iteration step. But if you believe for a second that the solution of this problem here is going to be something like a linearized Kerr metric plus decaying stuff, some of the linearized statement of this, then you would say, well, G1 is equal to a Kerr metric plus somebody telling you how to adjust the Kerr parameters. So it's again a Kerr metric plus something decaying, right? And so then the next linear equation you have to solve is again equal to the linearization of Ricci around the Kerr metric plus some decaying stuff. OK, so and then Richard told us how to go about doing such things. So you do two things. One is high-frequency analysis, symbolic analysis for the operator on the whole manifold. That gives you some high regularity control. And the second part is to analyze the model problem at, in this case, future infinity, so up here. And that model problem is, again, because the metric decays to a Kerr metric, the linearized Kerr stability problem. OK, so somehow one should think of what I'm going to talk about as some kind of normal operator analysis from the point of view of the nonlinear problem. All right. So, OK, so in case you had a rough night yesterday, I'm just going to write down theorem 0, and after that you can take a nap. So the theorem that we prove, so with Häfner, myself, and Vasy, so it should land on the archive in a week or two, is the following, namely the linearized version of this conjecture holds. OK, linearized, let's call it linearized conjecture holds. And so what I mean by this is if you have now initial data gamma prime, k prime, so they're just symmetric 2 tensors now in sigma, right, that being the tangent space to the space of Riemann metrics. So if gamma prime and k prime satisfy the linearized constraints, so what are the linearized constraints? Well, you linearize the constraints around the initial data of a Kerr black hole. OK, so they satisfy this linearization of the Gauss-Codazzi equations. Then there exists a solution H of the linearized Einstein equation, so linearized around the Kerr metric. And that attains these initial data in the sense that the linearization of this initial data map gives you gamma prime and k prime. And moreover, we show that H is equal to a linearization of the Kerr family. So let me just write down linearized Kerr. I'll write it down more precisely later. Plus a polynomially decaying term, so H twiddle, which decays like t star to the minus beta. OK, and so I'm going to give a more precise statement later. But this is just the complete sort of linearized analog of this conjecture. Okay. Okay, so any questions about the statement? Did I make a typo? Okay, so this theorem is, okay. So let me actually wait with giving references. So there are versions of the theorem which have been proved until I state a better version of this actually. So wait for it. Okay, so let me just talk about how we set up the solution of, the proof of this theorem. And the first step, as indicated, is gauge fixing. And so I've talked about this a few times before. So let me just be somewhat brief. So we impose an extra condition on the metric G. And the choice that we make is the following. So it turns out one has to impose usually 4 extra conditions. So we define a one-form W of G, which you can take to be something like the wave map operator. I don't know if that has a good name, of the identity map. So you're just checking whether the identity map pointwise on your manifold M is a wave map when equipping the domain with the metric G you're looking for and the target with a fixed background metric. So you can also think of this as some difference of Christoffel symbols, few of them being equal to 0. The main point is this is a one form and depends only on G and its first derivatives. Okay, and you can ask for this to be equal to 0. And chances are, if you pull back the metric G by some diffeomorphism, the identity map is not going to be a wave map anymore if you change the metric of the domain in that way. Okay, so that's a more standard thing to do. And what you then want to do is not just solve the Einstein vacuum equation, but you want to solve it in the gauge that W of G is equal to 0. And of course, here you have then initial data, constraint equations, and so on. Okay, it looks like you have made your life much harder now because you're supposed to solve 2 equations, not just 1. But it turns out that this is essentially equivalent for data arising geometrically to just solving a single equation, which is in addition much more well behaved. So it's equivalent to an initial value problem for the operator, I'll denote P of G, which is equal to Ricci of G minus delta G star of W of G. Okay, so delta G star is the symmetric gradient. Robin Graham yesterday called it capital D, same thing. Okay, so you're just putting these 2 things together in this fashion. It turns out it's equivalent to this, and roughly speaking, the left arrow here uses the second Bianchi identity. So let me just very briefly explain this. Namely, the Ricci tensor of any old metric doesn't have to satisfy any equation. Satisfies a first order PDE, because you remember that the divergence of Ricci is equal to twice the gradient of scalar curvature. So that's the second Bianchi identity. So you can hit this with something like the divergence operator that kills Ricci, and you end up with a second order equation for W of G, which turns out to be a wave equation. So some second order thing. Only thing it could possibly be is a wave equation. And then you can arrange things such that this W of G vanishes initially by arranging this gauge condition initially and using constraint equations and so on. And then you can conclude that this W of G satisfies a homogeneous wave equation with vanishing initial data, so it must vanish identically. And you're back from a solution of this to a solution of this. So that's a super rough picture of it. Okay. So let me just write that down here, that you get a second order wave equation for the one form W of G. Okay. So now, because we're looking at the linearized problem here, I'm just going to take that board over there and just put a bunch of derivatives in front. So the linearized version is then the following. So you want to solve the linearization of Ricci curvature around a Kerr metric, G sub b, and you apply it to some symmetric 2 tensor H, and then again you have plus initial data, the linearized constraints in the context of this theorem 0. And you also want to satisfy a linearization of the gauge condition. Okay, so now it's a first order linear operator acting on a symmetric 2 tensor H. And this again is essentially equivalent to using the linearized second Bianchi identity to solving an initial value problem for the operator I'll call L sub b applied to H. So this is just the linearization of your nonlinear operator applied to H equal to 0. Okay, so an initial value problem for this. Okay, and so this equivalence only holds if the initial data indeed satisfy these linearized constraint equations. So there's some extra PDE in the background. But in fact, what we'll do is that we will study this equation here for general initial data. So we somehow at this point forget about wanting to solve the Einstein equation. We're just interested in this very particular operator here, which turns out to be a wave operator on symmetric 2 tensors plus some lower order terms. Okay, and so if you understand solutions of this equation with general initial data, nothing geometric, then you in particular understand the initial value problem for the Einstein equation. And that's particularly useful actually for nonlinear applications because later on in this iteration scheme, these metrics around which you linearize don't solve any equation. The right-hand side here is just some weird symmetric 2 tensor. So you in general expect to have this kind of more general picture. Okay. Okay, so I'm almost ready to state theorem 1, which is theorem 0 upgraded. So the definition, just notation, is the following. So what are these linearized Kerr metrics? Well, you start with the Kerr parameters, M and A, and you take linearized guys. So this is really just a vector in R4. And then you define, so G sub b, the Kerr metric, linearized in the direction b prime. And this is equal to, well, you just take the Kerr metric with parameter b plus s times b prime. So you just wiggle the parameters a little bit and differentiate in the parameter s. Okay? And so this is a particular solution of the Einstein vacuum equation. Right, it just follows you have a family of solutions of nonlinear equation. That means that the linearization of the family solves the linearization of your nonlinear equation. Okay, so that's the first definition. The second definition, just for a little bit of honesty in function spaces. So remember that x0, which is gone now, was most of R3, except I cut out a little piece near the origin where the black hole was sitting. And so then I define x to be the radial compactification of x0. So it lies inside the radial compactification of R3. And, well, so rho, which is R inverse, is a boundary defining function. Okay? And then we'll work with B Sobolev spaces that have two parameters, S and L. So L is the weight. It tells you how fast objects in here decay, so rho to the L times HSB. S measures B regularity, okay, and the normalization is such that Sobolev space HB0 of x is equal to the L2 space of, well, on x0 inside R3 if you equip this with the volume, with the B volume density. Okay, so the point then is simply that Sobolev embedding complete overkill with regularity here, of course. Tells you that the weight here is indeed exactly the same as the pointwise decay rate. Okay, so this works, I think it's a theorem due to Sobolev that this works with infinity replaced by 3/2 plus epsilon. Okay. All right, so now for a better version of the main theorem. So again, same paper. And it's now the following. So let alpha be a decay rate between 0 and 1. And let's take two pieces of Cauchy data for a wave equation, right? So this is H is a symmetric 2-tensor on a space-time, so it's a 4x4 matrix, which is different, by the way, from the initial data for the Einstein equation, where you have this more geometric picture. You prescribe geometric data on sigma, which are sort of 3x3 matrices. Okay, so you give yourself H0, which let's just say is infinitely regular and decays with rate 1 plus alpha, and it lives on well, the compactification of sigma, but is valued in symmetric 2 tensors on the space-time. Okay. And likewise, you give yourself a piece of data H1, which decays like 2 plus alpha. So there's somehow typical scaling for wave equations on asymptotic flat spacetimes. And then, then the solution of the initial value problem, so LB applied to H is equal to 0, H restricted to sigma, and the time derivative of H restricted to sigma equal to these given initial data. So that now has a unique solution, no gauge issues anymore, it's just a good old wave equation, is of the following form. Namely, there exist linearized black hole parameters B prime, as in the definition. And very interestingly, there exists a one form omega, which lies in a fixed, so what do I mean by fixed? It only depends on the black hole parameters B of the Kerr black hole around which you're linearizing, but it does not depend on H0 and H1. So it lies in a fixed 6-dimensional space of one forms. On M, such that the solution has the following form. I can feel the excitement that you're just waiting for me to write down how that matrix looks like. All right, what is it? So H is equal to, okay, so it's equal to a linearized Kerr metric plus, so there's a one form, you can make a symmetric 2 tensor out of it by taking the Lie derivative along it, which is the same as taking the symmetric gradient of the one form, plus H twiddle. And H twiddle is decays like this, so it's bounded by some constant times T star to the 1 minus alpha. So you get as much time decay as you had spatial decay to begin with. And then you have R to the minus 1. Okay, so this is valid in T star positive. Okay, so the R to the minus 1 here is the typical decay rate for waves on Minkowski space, 1 over R. So that's some of the radiation field over here. But the interesting part is that you have time decay at a certain polynomial rate. Okay, so the what's funny about this is that this is just some semi-random wave equation symmetric 2 tensors with no geometric content if the initial data are just something. And yet the solution always has to leading order this kind of geometric behavior and then some decaying rest. Okay. But in particular, this holds, of course, if the initial data do satisfy, do come from some geometric problem. Okay, and so in reality, of course, this H twiddle lies in some weighted space-time Sobolev space on that space over there. But I'm going to walk you down a notation. Okay, so what's the 6-dimensional space here? Well, omega lies in the span of the following kinds of things. So I'll call it asymptotic translations. By which I mean omegas which are of the form dxi plus some decaying stuff. Okay, so these are basically one forms or vector fields that just translate in a certain coordinate direction. So that's a 3-dimensional space, and then you have also asymptotic boosts. And that means something like t dxi minus xi dt plus lower order terms. Okay, so the sign looks funny because I'm switching to one forms instead of vectors. Okay, So that's another three-dimensional space. And I'm lying just a little bit. There's some extra dimension, but you can get rid of it. OK. So what's nice about this theorem from the point of view of the naive nonlinear iteration scheme I was talking about is that from the linearized solution, you can read off how does the black hole want to change its mass and angular momentum. And you can also read off from this one form omega, where does it want to go? Right? So you somehow see that the black hole may want to just shift its center of mass a little bit here and then start going off with a certain fixed velocity towards infinity. And so then you can, in a nonlinear scheme, try to change the gauge to just sort of rechange your coordinate system so that it actually remains fixed at a fixed point in in space. OK, so that's somehow very nice.
What about asymptotic rotations?
Very good question. So yeah, they can be subsumed actually into here, because if you have a black hole that's rotating around this axis and you rotate it a little bit, then it's the same as changing the black hole rotation axis by a little. Yeah, so you could subsume them, but then it would not be. There's some direct sum here of asymptotic solutions. That would not be a direct sum, but just give you linear combinations of the things that are already on the blackboard. OK, so I'm running out of time much more quickly than I thought. So let me just mention the very recent work by Anderson, Beckdahl, Blue, and Ma, who proved this when the decay rate of the initial data is, I think, bigger than 5/2, in which case so they study the linearized Einstein equation, so not this generality, but really just for geometric initial data, in which case the final black hole linearized parameters are equal to 0, so these solutions don't actually have any stationary component, they just decay, period. And then there has been lots of previous work by the Rodniansky, Tom Johnson, Hong, Keller, and Wang, sort of in 16, 18, for the case that you look at a perturbation of a Schwarzschild spacetime. OK, so how much time do I have left now?
3 minutes.
OK. So yeah, just integrate by parts twice. And OK, so obviously I can't actually give you the proof. But so here it is nonetheless. So you recast it as, so Alex told you how to do that. You recast the initial area problem as a forcing problem. And then you just write the solution as the inverse Fourier transform. So I just taught microlocal analysis, so I know there's a 1/2 pi here. And then you integrate just over the resolvent applied to the Fourier transform in time of your guy here. I did teach it, but here the sign convention is funny, so this is OK. And so C here is very positive, so a priori the exponential here is exponentially growing, but then you shift the contour to the real axis. And then what happens is that you have to show that this inverse here doesn't have any poles, except at sigma equals 0. And at sigma equals 0, the resolvent will look something like, so you actually have an explicit leading order term plus some regular part of the resolvent, which, however, only lies in some like 3/2 minus something for sigma near 0. OK, so the low energy resolvent, the regular part of it, only has finite regularity. And that regularity tells you what the decay rate becomes. So it's very important, though, that I just mentioned a few names here. So the input that goes into this theorem is, so most of it is just general theory about this Fourier transform operator here. And so it's like an asymptotically Euclidean resolvent, more or less. And so for that, we use work by Melrose, Vasy, Zworsky, as in Jesse's talk. So that's about the radial points at infinity. Then there's work by Vasy and a little bit by myself near the horizons. So near the horizon, there are some radial point estimates going on there. And then work by Zworsky, Dietrich, and myself on trapped set. So there's something very interesting happening with orbiting photons. And for the low energy part, I want to mention work by Guillaume and Hassel, and also Sikora, where they construct the parametrics for the low energy resolvent, or construct the inverse very precisely. But we instead use something that Andràs did, which is about to be published, which is about Fredholm theory for low energy resolvents. Okay, so ultimately, we do explicit calculations for Schwarzschild and then use very robust sort of microlocal techniques to perturb to Kerr without having to do any separation of variables for the Kerr spacetime, which is very pleasant. Okay, so one thing that you may notice when you look at this list of people here is that with a few notable exceptions, they're all Richard's PhD students or grad students. I mean, whatever, grandchildren students. Okay, so thanks for being so productive. And just one very final thing, I suppose I'm out of time. Something very funny happens, very intriguing. Namely, so, right, the main part here is to study the resolvent. So let's call it the resolvent for black hole parameters B on spacetime M. Okay, so 0, I told you, is a special place, but it turns out that the spectral parameter 70 is much more interesting. And so it's it produces a piece of cake instead of an operator. So thank you very much. Happy birthday.